Anyhow, so now if I'm going to be on the camera, I'll be over here. So, as mentioned by Nels, I'm Carl Richter. I'm the programs chair for this year, and hopefully next year, assuming we have two more sessions. And our session tonight, we're lucky to have three gentlemen from Los Alamos. They're going to talk about their CMM techniques that they use there. And they found a methodology that saves them time and money. And one of the things we did prior to starting our presentation at all was they agreed to meet with a local small business, Sun Country Industries, that makes parts, aerospace parts for GE and others. And we wanted to see if their technology might be transferable to Sun Country. So we gave it the college try, and I guess at this point, they've not totally agreed to do something like that. They have issues with it. So we'll just say that thus far, we've not succeeded with that. But I'm going to start off just mentioning a few things that I think are important for one to do, as I suppose in that, to have a good program where you have an overall scheme. What's this? Okay, for CMM. And so I'm calling it a scheme for CMM use with the gauges and the tools for reducing your costs and improving efficiency. Let's see. I got to see how this works.
Good.
Okay. Yeah. Okay, so I see that there are basically 5 areas that one needs to address when you're doing this sort of thing. First of all, you've got to define key factors, and I'll show you a table in a minute where independent variables, those are the variables which determine what the CMM machine is telling you, is measuring, have to be understood. You have to understand the key factors there. And then you can use brainstorming, cause-effect analysis, various methods to come up with the independent variables. Then you characterize the relative importance of those to the CMM tool that you want to use for your measurements. Okay, then you perform a reliable repeatability and reproducibility methodology where you test the gauges and the tools with the CMM. And then lastly, you determine the CMM capability plan, and then you perform experiments whereby you determine the distribution of your test results. You might have to measure, is it normal? Is it, you get the X bar, the standard deviation, all of the usual things, midpoint distribution. So you do things with your control charts, CPK, and then CP. CP is your capability of the process, as you all know, and CPK is the capability of your measurements from the CMM relative to the specs and so on that you have for your tool. And then lastly, when you get to that point, you want to optimize it. So that means you do a variety of iterations to reduce the variation and increase the central tendency.
Hey, Carl?
Yeah.
Somewhere in that last line is Z.
Z
Talking
statistic.
about impedance here or something?
No,
else?
Z is a statistical terminology. I'll show you what it is in just a minute.
Okay.
As it relates to, say, a normal distribution. Let's see. See, I'm not sure how you go south on this thing.
Every discipline
Use the
has
arrow
its
key.
own
Use the right arrow key.
terminology.
Oh, maybe it's this. Okay. Well, anyhow, so this would be the type of table. Now, this is only for information only, and doesn't look too good here. But basically, here's your output for the CMM, your what I call dependent variables, and you might have accuracy, precision, whatever the tools are. And these are numbers I've just put in there to show you how it might look. The CMM input might be its squareness, its linearity, its vertical straightness. There's a variety of things. And typically, there'll only be 4 or 5 or 6 key factors here that have the biggest effect on these output variables. So that's the main thing I wanted to show here. Okay. So assuming this is a normal distribution, my art's not so good. But once you've characterized the CMM gauges, then you want to compare the output from the CMM tool with your specifications and so on. So there's a real value. This comes from a standard or whatever for your measurement. This would be the average of some measurement, and then you've got some variability around it, your standard deviation. And typically, the literature that I've read says you want you want better than equal to 2% measurement capability versus your measurement. You want the tool to be that good. And you want the CMM to measure less than 0.1% of product tolerance. Is that kind of what you guys do? Or better than that?
Yeah, that's the old gauge maker's rule. 10%.
That's the old
Usually,
rule?
What, 4 to 1?
4 to 1? Okay.
Yeah.
So you do better. And so, anyhow, here's some definitions. You see CPKs and CPs. These are the definitions for a normal distribution. Let's see.
Got it.
Oh, go up. Okay. I jumped ahead. Okay, so this is my last slide pretty much.
Can we expand that screen?
Yes.
Click on the little screen icon on the bottom right, it'll be a presentation.
Where is it?
Right, is it the percentage on the number on the bottom?
See the
Is
percentage?
it 45% to the left
Ah.
or 45%?
One left to that.
To the left of that.
Here?
Yep. That's it.
Oh, thank you.
Now it's next arrows will lead back to.
Okay. So anyhow, so again, the CPs and the CPKs, I have a table here which shows the reject rates. If you're talking about leaving data at the tails, you want your distribution to be tight and in the middle of your upper and lower limits. So say a CP and a CPK of 2, you can see that the reject rates will be very low and it's very centered. Okay, if you have something like this, you see that there's a tail outside the upper and lower spec limits, so you're going to lose theoretically some rejects there, so you don't want that. And then if you have a shift in your distribution like this, then you're going to reject even more. So I think the only point I'm making here is that when you get to the point where the CMM has been somewhat defined and you've got it centralized, then you want to reduce that variation and you want to center it, and then you'll get the best result you
Is
can.
that the quality of the product or the quality of the measurement?
Well, this would be using a product, they're going to show you how to do the calculation, but you can break out the quality of the tool as well as the parts. And there's a way to do that. So that's all I'm going to say, and I think these gentlemen have a lot more to say than that. Now how do you do this?
What was that? Browser and my
Okay, so we have two of the twins, Mario.
Yes.
I don't know if you noticed that, and Lucas, and they are twins, and they both have PhDs in mechanical engineering. Okay, and they've been doing this for about 10 years, right?
Right.
And then Joshua, who's their fearless leader, has been also has a master's degree in mechanical engineering. And so all three of them at Los Alamos have been working in this area of
Right.
CMM machines for a long time.
Yeah, for
So,
over 10 years. So.
10 years. So without further ado,